Ethan, are you taking a programming course?
Yeah, I'm in Principles of Programming. I'm in
110?
yeah,
Okay.
and then I've also taken Java in high school.
Taking,
I've taken Java in
yeah.
high school.
Oh, you did?
Mm-hmm.
So 110's probably kind of easy for you
Yeah,
because it's all review.
most of it's review. I'm learning some new stuff though,
Yeah,
especially with how C++ works.
yeah. So then as an EE, do you take CSE 205, the course that follows 110? No?
I don't know. I know that I have to take some assembly language stuff.
Oh, 230. Yeah, CSE 230. Are we ready? Yeah? Okay. Well,
I'm really interested in programming though.
are you?
Yeah.
That's good. It's a lot of fun. So let's see here.
Oh, I'm actually in CSE 100 right now, not 110.
That's what I thought when you mentioned C++, because 110's Java.
Yeah, I'm in CSE 100. And then in high school, I haven't touched Java since I got here.
Okay. Yeah, 100 is required for EEs. So then you'll take CSE 230 at some point, EEE 230.
Mm-hmm.
And if you wanted to, if you're interested in sort of continuing your programming education, then after you finish CSE 100, you could enroll in CSE 205. So for the CS students, they take 110 and then 205, which is just a continuation of 110. It's in Java. But the prereq for 205 is 110, but if you get a C or higher in 100, then you can petition to enroll in 205. And you'll go into more advanced programming concepts, but it'll be in Java as opposed to C++. Yep. So I was going to open the lab manual that I wrote again. And is there anything in particular you want me to go over?
I don't know. I came here.
Or I could just show you some things that might be useful, but if you have some things you're interested in learning that I can answer, we could talk about that.
I'm not really sure what to learn yet. Eventually, I would like to go over bash scripting,
Yeah?
but like if you want to go over just stuff you think would be helpful first, that would be fine.
Okay. I do hope to get the bash scripting workshop set up in the spring.
Okay.
So one thing I thought would be useful then is in section 9, I've got a section here on I/O redirection. So this is common and very useful at the command line. So let's talk about that. Let me see if I can navigate to that page. Guess I can't. There we go. Nope, wrong one. There we go, page 49. So when your program starts up, there'll be 3 files that are created by the operating system and they're associated with your program. And those 3 files are referred to as standard input, standard output, and standard error. And the abbreviations are those. So for standard in by default is attached to the keyboard. So whenever you type at the keyboard, it goes to standard in, and then standard in feeds it into your program. Standard out is attached to the console or your terminal window, and so is standard error. So if you're writing C code and you do a printf, it's going to go to standard out and it's going to go to the output window. In C++, cin would read from standard in and cout writes to standard out. So sometimes you have a program that you would like to, instead of you have a program that sends the output to an output to the console, but there's times you would like to send the output instead to a file. And so you don't necessarily want to modify the code to make it send the output to a file, because other times you may want it to send the output to the console window. So we need this sort of mechanism so that we can do both. And you may not even have access to the code, so you might not even be able to modify it in the first place. Echo is a bash command that when you say echo, it sends the thing that you print, the string, it sends that to standard out. So if you're running a bash script, echo is kind of like printf or cout. Okay. So to redirect the output from a program, you can use a greater than symbol. So in this case, I've got a file named file01.c, and normally when you cat, it will send the output to the terminal window. So cat is a command that you can use to just send the contents to the output window, to the terminal. If I want to send the output to a file, I do greater than, and then I give the name of the file. So if you want to try that out with something. And so this is called I/O redirection. So we're redirecting the output from the terminal to an output file. Let me go ahead and I'm going to go to General, and oh, I don't like VI. I'm going to create a little C program so I can illustrate some of this. Did you get it to work? Okay. I'm creating a C program so I could illustrate. Yes. So this is C, and standard IO.h is the C equivalent of IOStream. In the C standard library, the various header files end with a .h file name extension, H for header. In the C++ standard library, they got rid of the .h part, and you just, if this were a C++ header file, you would just say standard IO. Yeah. And then main is your starting point. I've defined a couple of int variables. In C, scanf is how you read input from from standard in. So this statement, this first one, will read an int. The %d says read an int. So it'll read an int from standard in, and then we do the same thing, and I read an int from standard in. And then I just compute the sum, and then printf is your C++ equivalent of cout. So I'm going to run this program, and the first time I run it, I'll just type my numbers at the keyboard, and it will output the results to the terminal window. So let's save this. Oops. Oh, I hope I didn't just lose that. I just lost it. I can do this. Give me just a sec. Have you studied any C code? Oh, okay. I didn't know if you'd had a class in it. Yeah. Oh, that's neat. Oh, what site is that? You don't know? Oh, cool. That sounds fun. I'd like to know about it. If you can think about it, send me a link and an email message, because I like to collect websites like that I can use for education. Okay. Yeah. Okay. Does this code all make sense to you, or you want me to explain anything? Let me see if I can save this. Yep. So scanf, I'm not sure, this should be scanf. Scanf is equivalent to cin, so you're reading from standard input. Scanf, F stands for format, so you're reading formatted input. So the syntax is you give it a string, and the string contains what are called format specifiers. And if you want to specify that an integer, you use %d. So this %d is a format specifier. Yes, right. So this says read an int from standard in, and you put the value into a variable. And scanf expects the address of the variable. So ampersand in C and C++ is the address operator. So that says put the value in the location where A is at. And then I turn around and do the same thing with B. And then printf stands for print format. And so same sort of thing. This will print sum equal, and then the %d says print an int. And then following the string, you have a list of variables that you want to print. So if I had if I had multiple variables, I could say A equals %d, comma B equals %d, and then sum equals %d. And so then I can say print AB sum that way. So now let's save. Let's Control O, and I'm going to build this. Now this is a C program, so we use GCC, which is the C compiler. You can specify the name of the output. Well, let me just compile it. Yep. So when I build this, notice that it creates, let's see, hold on, I'm in the wrong place. I'm going to move my file to a temporary directory that I can delete later. Oh, in your terminal, you can use the up arrow and down arrow keys to go up in your command history list and down. Are you aware of that? Okay. Another thing you can do is, we talked about history. So if you type history, it'll give you a history of all of your commands. Yeah. And they're in order, so these, if I pipe that through less so that I can read all of it, this goes back to, looks like 11.6 at 1831, and then I did a bunch of commands, but at the bottom of this, at the very bottom, is the last command that I executed, which was actually history. So if I want to do the GCC again, that's command number 1004. So I can do exclamation mark 1004, and it'll repeat that command. Now another useful thing that you can do is I just repeated the GCC command because I said here to execute the instruction or the command that's in my history list at 1004. Another thing you can do, which is real convenient, is if I know that the last command that I typed that started with G was GCC, then you can just do an exclamation mark G. This will go back in your history list and it finds the first command that starts with G and it'll execute it. So if I do exclamation mark G, it does the same thing. So like if there's say a cat command, if I want to do that cat command, I can just type C or CA. If you have multiple commands that start with C, so let's say there's a cat and there's a CP. If I just say exclamation mark C, it's going to execute, actually it's going to execute that one. If I want to do cat, I can do exclamation mark CA. And then it will go back and says, well, not that one, there's one. So that's real convenient. Okay, so I built my program and it produced a.out. And if you want to give your program a name, then you can do -o, and I'll call this program. And then you can specify the name of the file that you want to compile. And we can probably build this with the C++ compiler because C++ is based on C. And I've read that it's not strictly true that you can think of C as being a set and think of C++ as being a set. Well, the C set is contained within the C++ set, so C is a subset of C++. That's not really strictly true because there are some differences. Yeah, but basically a C++ program compiler will compile C code most of the time. We talked a little bit about the compiler options last week, so I think that was in chapter 12. No, that's shell scripting. Chapter 13 is where I talk about developing programs using GCC. I was going to go through here and see if there's any compiler options. Because you could start doing your C++ programs. Are you doing those now in Linux? Yeah. And then build? Yeah. Okay. Okay. You want me to show you a little bit about that? Yeah. So if we want to use the debugger, you have to build your program with -G. So do you have a little program that you can compile and debug? Or while you're doing that, I'm going to modify my program a little bit to add some more stuff so that we can debug it. Uh-huh. Oh, yeah. Actually, I'm going to do this way. Oh, let's put a loop in here. Yeah? Yeah, let me show you. So you want an array of integers? Okay, and you know what the array needs to be initialized to? The initial values, is that what you're asking? Okay. So in C++, you would write, well, there's two types of arrays in C and C++. There's statically allocated arrays, which is what you're going to study in 100. And then there are dynamically allocated arrays. So I'm just going to talk about statically allocated arrays because that's what I think you're probably talking about. So you would write int for the data type and then the name of the array. Let's call this the array. Then you put in brackets the size. So that line of code would say at runtime there will be a block of memory allocated for this array. There'll be 10 elements, each of which stores an int. You can initialize it later. So this simply allocates the array. Every memory location in your computer stores a value, and the value is what value was written there the last time by some program. So when I define this array, there are values in these elements, but those values are just, we call it garbage. So there's garbage in those values because we never initialized it. Now, when you define an array, you can initialize the elements at the same time if your array is small enough. Well, it depends on how you initialize it. So let's suppose I want to initialize every element to 0. Then I can basically just say here, I forgot the syntax. Hold on a second. I want to make sure I'm telling you the right thing, and I've forgotten the syntax off the top of my head. Because it's changed in newer versions of C++ than it is in the older version. There we go. This is a really good website on C++. It's called cppreference.com. And it's a little technical, but it's a really good reference site for C++. So there are different ways you can initialize an array. And so after you create your variable, you can say equals, and then in a pair of braces, you can list the initial values. So going back to my program, I could put this here. And that will initialize, because I only list one value, but the array has 10 elements, that'll initialize all 10 elements to 0. No. Now, finishing this example, if I want to initialize the elements, all 10 of them, you can just enumerate the values that you want to initialize it to. So something like that. A statically allocated array is the word static in programming language terminology generally refers to something that happens at compile time when you're building the program. The word dynamic refers to things that happen at runtime. So this is a statically allocated array because we specified the size of the array here, and at compile time, this array will be, we've specified that this array will have 10 elements. Once you statically allocate an array, you can't change the size of it. what you would have to do is create a new array that's the new size that you want, and then copy the values from the old array to the new array. You want me to show you how to do that? Okay. Okay. In fact, I'm gonna go ahead and I was going to put a loop in here, so let me just do that example anyway, because I wanted to write a loop. So let's create a function. Now my array is ints, so I'm going to create a function that I'm going to call this resize array, and the input will be an integer array. So we specify that the array is an argument. You write in your function header, you write int and then the name of the variable that you're defining, and then you just put bracket bracket. You don't need to specify the size of the array in the function header when it's a one-dimensional array. So this function is going to create a new array, and I'm going to return that new array. So I can specify that the return value is an array. Now, I'm going to switch, and I'm going to turn this program into a C++ program instead of using C. So let me, I'm going to switch this so that we're doing C++ code. So then, instead of using scanf, we'll do cin, and then instead of using printout, we use cout. Okay. Now, one thing before we go on, I presume your CSE1 instructor has taught you to do this using namespace standard line. Right. Do you understand why that's necessary? Okay, good. Because I did want to tell you that if you don't do that, then you refer to cin as standard : cin. And then we refer this to be standard : and then this becomes standard : cout, and that becomes standard : indel. We teach the students in 100 to use the using namespace standard line, but honestly, that's kind of sleazy, and it's not really recommended that you do that. Now, we teach you that in 100 because it makes it easy. Because if you don't do using namespace standard, then you've got to always preference cin and cout and indel with standard : I don't really remember the arguments. I've just read online that people argue at that the using namespace standard line is sort of sleazy. And I don't really remember right now off the top of my head why. Well, one thing it does is, so standard is a namespace, and a namespace is just a collection of identifiers, names. So when you do using namespace standard, then suppose within this standard namespace there's a variable called foo. It's an int. So if I put this back, well, let's suppose this. Suppose I've defined a variable here called foo, which is an int. If I have the using namespace standard line here, that essentially sort of imports all of the names that are part of the standard work namespace into my program. So now what will happen is, because there's within this namespace there is a variable called standard foo. Well, now that variable name is going to conflict with my variable name here. So what's going to happen would be that the compiler, well, I'm not sure what would happen. I think the code will go ahead and compile, but it can lead to conflicts with names, because your program, your identifiers are in their own namespace, and then you've got standard, and you could have a program that uses other libraries, and so you could be using, a half a dozen namespaces at any one time, depending on the libraries you're using. And when you do using namespace standard, you import all of the names into the local namespace here, and that clutters things up and can cause problems. So if you don't do that and you explicitly say standard : then this doesn't import all of the names in that namespace. It just imports the ones that you're actually using. So now I have let me finish resize. So in addition to passing in the array, I'm going to pass in the new size. So I want to resize this to a new size. So that'll be an int. And we have a situation now where new size is equal, less than, or greater than the size of array. Right? 3 conditions we have to consider. If new size is equal to the size of array, we just don't, we just do this. So let me go ahead and do that. Let's consider the case when new size is equal. So we'll create our new array. Oh, yeah. Let me try something out. I think this is legal, but I got to try it out. What I'm wondering, Ethan, is if it's legal for me when I say define an array. I think in certain versions of C++, it's legal to put a variable inside the brackets. So I'm just going to test that out because I'm not sure. I think you can. Oh, I'm going to rename my file too. Do you know how to rename a file? Yeah. So my program is program.c. If I want to rename it, this took me forever to figure this out when I started using Unix, because I was looking for a command named rename, and that's not how you do it. The way you do it is you move the file from the old name to the new name. So the move command is mv, and that allows you to move a file or a directory from here to there. So I just moved the old file name to a new file name. And now I've renamed my file. You can do that with directories too. So let me try to build this now, because I want to see if that allows me to put a variable there. Oh, Ethan, if you're going to debug code, you have to specify this compiler option. This one. You have to compile with -G if you want to debug your code using GDB. Let me show you a little bit about GDB still. Yeah, yeah. Well, I started on this track because you said you were interested in knowing more about GDB. So I don't know if you want me to go continue. I was just creating a program that we could debug. Okay. But to debug, you have to pass -G as an option when you compile. So I'm gonna do -O. I'm gonna do -G first, and then do -O, the name of my program binary, and then the name of the file that I want to compile. Oh boy. You see those error messages? When you get 1,000 billion error messages like that, it's usually because you're doing something wrong with a stream. And C-in and C-out are called streams. So let me pipe this through less so I can see what the first message is. So on line 23 and column 63, it's, oh, I see it right there. You use angle brackets pointing, let's see, from your perspective, it would be that direction to send stuff to C out. But notice right there that I oriented the brackets the wrong way. So I need to fix that mistake on line 23. Oh, I thought that would load my file. Oh, I know what happened. I renamed the file. Yeah, that should be pointing that direction. Now it's complaining. Oh, it doesn't like the int bracket that I put for the return type from our resize array function. I wasn't sure if that was legal or not. The standard way of specifying that you want to return an array from a function. Now, I don't know if you've looked at pointers, if you're familiar with them. The standard way then is we say int star. Int star is speak for pointer to int. And an array, when I create an array like this, what happens is this variable, the array, basically points to the beginning of the array in memory. It contains the address of the first element. So this basically then is how we can say that we want to return an int. We're returning a pointer to an int, but the name of the array is a pointer to an int. Yep. Now this worked, so it is legal for me in this version of C++ to put a variable there. So now that I'm in good shape, because now I can say create a new array, which is new size in size. And then I need to copy the elements from the old array to the new array, which I can do with a for loop. Oh, we have another problem. In C and C++, when you pass a one-dimensional static array to a function like we've done, right? Well, we haven't called this function yet, but when we do, we'll pass this array. We don't know the size of the array. We also have to pass another variable which tells me how many, what is the size of array. So I'm going to pass another int, which is called, let's call this array size. And then let's set up a function call here. So let's create an array. Oh, we have already got one right there. Let's resize this array. So we'll call resize. Let's make the new array 10 just for the time being. Then the second argument would be the size of the existing array, which would be 10, and then the array I want to resize, which is the array. And this function is going to return a pointer to an int. So I think I can do this. I'm not sure. I'll have to try to build it. Oh, I need to say brackets here. Yep. So we'll just copy the old elements from the array to the new array. Let me finish typing what I'm typing in, then let's discuss that. So new array sub I is going to be equal to old array sub I. And then at the end, we'll return new array. Okay, so what will happen is that statement, when it's executed, allocates the array. It initializes each element to 1, 2, 3, so on. Then this statement we'll call resize. The first 10 is the new size of the array that we're creating. The second one is the size of the existing array that we're creating a duplicate of or resizing. And then the third one is the array that we want to resize. Now, let me save this and try to build this. And if it builds, then we can start trying some debugging. And I have some syntax errors. Okay. So I've got 3 syntax errors I got to fix. One is caused by that. One is caused by this. The other one is a little bit subtle. Let me try building this again. Trying to think how to fix this here. Yes. You have bool, B-O-O-L. Yep. Oh boy, this is just getting worse and worse. Well, here's another well. Here's what we can do. I'm having a problem returning this new array from the function. It's not taking it. So what we can do is I'm going to change my argument list. So I'll pass in the size of the existing array that I want to copy. I'm going to call this old array. And then I'm going to pass in the new array size. And I'm going to pass in the new array. This way. And then I'm going to make this a void function. And get rid of that return. Yeah, this is difficult. Yeah. I can make it work. It's just taking me too long. So let's just create something else just so I can show you how to get into the debugger and do some things. The short sort of answer would be that if you know that at some point you're going to create an array and you need to make it bigger or smaller, don't do a statically allocated array. Use dynamic allocation instead. Now, if you want to dynamically allocate an array, then suppose the array is my array, but I don't want to statically allocate it. I want to dynamically allocate it. Then what I can do here is say that let's try this. By the way, there are different versions of C++. The most recent version that's been published is 17, C++ 17, which came out in 2017. The newer version will be C++ 20. It's supposed to come out next year. My C++ knowledge is primarily C++ version 98 because for what I teach in CSE 100, we just cover sort of the basic stuff. And so a lot of the newer features that have been added to the language since 1998 are things that we just don't really use in CSE 100. So I'm trying to, I'm doing this as if I'm writing 98 code because there's probably different or possibly better ways to do this if I were using a newer version of C++. As far as I know, the 1999, and then I think there's been another one since then, but I think everybody uses 1999. Yeah, that's known as Standard C or ANSI C. C++ is 2017, I think, was the last one, and 2020 is supposed to come out. Yeah. The language C hasn't changed a whole lot. Yeah. So the way you dynamically allocate an array is I'm going to create a pointer, because an array variable is simply a pointer, a memory address. So then you do equals new, and then you specify the data type of each element, which will be an int. And then you specify the size of the array. And here is where I'm not sure because I don't know. Let's go to that one web page as I was looking at. Well, I don't remember the syntax for how I initialize this. Well, actually, that's C anyway. Well, that's all talking about dynamic arrays. On your program, you would do change mode, chmod, and then plus X, and then the name of the file that you want to put the X permission bit on. Okay, here it is. So it says prior to C++11, there was no easy way to initialize a dynamically allocated array. This would be the way you would have to initialize it. And then, okay, so that's the new syntax. Okay. So now let's just write a function that prints out the elements of the array, just so we have a loop we can debug. Oh. Ah. Oh, here's one thing you may want to be aware of. When you build your program using G++, by default, it compiles there's different, as I mentioned, there's different versions of C++. So when you compile using the GNU C++ compiler, you can specify which language version you want to build your program. And you do that. So notice that I'm getting an error message in my code here because I've dynamically created my array, and then I have my initializer list here. But this isn't legal in the version of C++ that the compiler is the default version. The default version is basically somewhat equivalent to C++ 98. So I need to compile with at least version 11. So when I build my program, you can do, you would do on your command line, do std for standard equals C++ 11. Yeah, that works. So now, because that code won't work because it was using version 98, I've told it to use version 11. And in version 11, what I'm trying to do is legal, but it wasn't legal in version 98. So your instructor is most likely just teaching you C++ 98 because that's pretty much what we do in 100. But if he's teaching you some C++ 11 or advanced stuff, or if you just want to do it on your own, then if you want to use C++ 11, components or the language, then you have to specify which version. Yeah, I think so. The man page for G++ is a little bit hard to read. But if we find the standard option, now when you're viewing a man page like this, or you're viewing a file in less, you can search for a string. You just hit a / and then you type the string you want to search for. And then if you want to continue searching, you just keep hitting / until you find the actual location. So there it is. So the language standard, what does this say? There it is. Oh, that's C. There it is. The default language is, now the GNU compiler, they've modified some things, and so the GNU C++ compiler accepts some code that's not actually part of the C++ language standard. So the default one is GNU++ 98, which is the GNU implementation of C++ 98. But it contains some stuff that's not actually part of C++ 98. So that's what I thought. And then if you want to compile with C++ 11, then you just say that dash standard equals, and then you've got your C++ 11 option. Now I've got a program, binary, that I can debug. And to debug it using GDB, you just type GDB and then the name of your program binary. So do you have a binary that you can load? Okay, good. Now GDB is all text-based, so again, like the terminal, there's no windows or buttons or anything like that. But it provides the basic debugging features. Now I have in that manual, which you have access to if you go to devlang.com, I've got a chapter on GDB. Let me find that. And I think it's this, it follows chapter 13. It's chapter 14, I believe. There we go. Okay, so to start GDB, you type GDB and then the name of your binary. I specified the -G option. What that does is the debugger requires knowledge or information about the program, like the names of the variables, the data types of the variables. And that information's not available at the machine language level. So what the -G option does is it tells the compiler to put debugging information into the binary, and that debugging information includes things like the names of the variables, the names of the functions and stuff. You would never want to ship production code that's been compiled with the -G option, because it's going to contain a lot of information that your competitors could use to sort of back or reverse engineer your program. So, yeah. So, like if you were developing production code, you'd compile with -G while you're debugging and testing. And then when you're ready to release your product, you rebuild, but this time don't do -G, because that'll put a lot of information in there that would allow somebody to reverse engineer your program. You don't want to make it any easier for them. You can also, when you compile using the G++ compiler, and most compilers, you can specify that you want the compiler to optimize the code or not. And with G++, going back to, hold on a second. I want to talk about the optimization. That's in chapter 12 again, so that's on there we go. It's section 13.1.1.10. Here we go. So -O is how you specify the optimization level. What we mean by optimization is that the compiler, as it's reading the source file, is creating the machine language version of your program. And if you don't optimize the code, the generated machine language code may not be efficient. It may not run as quickly, or it may use too much memory. So you can optimize it, and you can specify different levels of optimizations to the GNU compiler. And what that does is the compiler will perform additional steps before it generates the machine language code in order to try to generate the most efficient code that it can. So optimization levels are 1, 2, and 3. And the higher the level, the more the compiler is going to spend trying to optimize the code. It takes time to do that. So when you compile with -03, it's going to take longer to build a project than it would if you compiled with no optimization. But in a production environment, you want your program to oftentimes run as fast as possible. So during testing and debugging, you don't want to optimize, but you may want to optimize when you release the product. Yes, -lowercase o is how you specify the output file name or the binary. So by default, -o is the -0 is the default. So we don't need to do anything, but I wanted to make you aware of that. Yeah, let's try that out. To get out of GDB, you just hit Q. So I'm going to compile my program again, and I'm going to specify, well, let me do this. I'm going to compile it, and I'm going to save the binary to, I'm going to move the binary to a different file name. And I'm going to call this binary program -0. Now I'm going to compile again, and this time I'm going to specify -O3 so that I can optimize it as much as it can do. And this time I'm going to call the binary program -O3. That's interesting. The one thing you can see is that with -O3, the size of the file is actually larger. And I was expecting it to be smaller, because you can optimize for time, or you can optimize for space. By space, we mean memory. So I was assuming that this would optimize by space as well as time. But anyway, let's see. We can look at the code. So if we fire up program -O0 into GDB, once you load the program, let me go to the GDB chapter again. So there are you can list the source code. So if you just type list, it will list the source code starting at the first line of main. Actually, it started at print array, didn't it? You can abbreviate list as L. And if you just keep hitting L, then it just continues displaying more of your code. So, and then eventually I reach the end of the code, and if I hit L anymore, it just says I'm out of range. Now you can list the code starting at a certain line number. So if you've got a big source code file, and there's a particular function that you want to debug, and you know that function starts on line 628, then you could do L 628, and then it would list the code starting at line 628. That's useful because when you're debugging, you want to see the source code, but you also want to be able to debug. What I usually do when I'm debugging is I have a copy of the, I open the source code in an editor window, and then I open the debugger in a different window. And then as I'm debugging, if I need to look at the source code, I just switch to the editor window. So I don't usually use the list command within GDB. So what else can we do? And there's different ways. So if you know the name of the function, you can just say list function. Examining the assembly language code. So this is often fun. So the disassemble, that's called disassembling. So when you write assembly language code, you assemble it using a program called an assembler. And then that generates the machine language code. A disassembler reads the machine language code and tries to generate the source code from it. So the command is disas. So let's try to, I'm going to go to line 16, which is the first line in main, and I'm going to try disas. Oh, no frame selected. I don't know what that means. Oh. You may need to start executing the program before you can disassemble it. Were you able to get it to work? Did you try that? I was trying the disassemble command and it says no frame selected. So when you load your program in GDB, it's not actually running right now. It doesn't run until you tell it to start running. And the way you tell it to start running the program, there's a few ways, but trying to find it here so I can show it to you. Well, I know it's in here somewhere. The way you start the program so that you can debug it is you type start. And then all of this verbiage basically says that right now the next statement that's going to be executed is this one, which happens to be the first statement inside my main function. If I list my main function, then this is just telling me that now that I've started, the first line that's going to be executed is that one. Now, you can run the program nonstop. You can step through it line by line. And the way we usually do debugging is if you have a bug and you don't know where it's at, you can just start stepping through the code, executing one statement at a time until you find it. It's easier to know if you have an idea of where the bug's at, like it's in this function. Because that way, you don't want to step through all the code and then get to that function. You just want to get to that function. So let's suppose that I just want to step through this code, executing one line at a time. The command for that, oh, I was going to try the disassemble first. There we go. Now it's working. You have to start the program. So this is a dump of the assembler code for function main. And once you learn assembly language, you could go through this and figure out what it's doing. But I wanted to look at that. And then I wanted to look at the disassembler for my optimized program. So I'm going to load my optimized program, start it, and disassemble main. So that ends at offset 226. So let's go back to the unoptimized one. Wait a minute, I was in the right one, wasn't I? Yep. So now I'm going to load the optimized one because I'm curious to see if main is shorter. That's the unoptimized one. Yeah. Start. Notice in the unoptimized one that it goes all the way to 232 and then it continues all the way to 284. So the main function in the optimized version is quite a bit shorter than the one in the unoptimized version. Okay, so what was I going to, oh, I was talking about stepping. Okay, so yeah, let's, I'm going to load the optimized version. Oh, let me load the unoptimized version. The reason it's hard, the reason you don't generally want to debug optimized code is because it sort of, it confuses GDB. Let's just put it that way. So I'm going to debug the unoptimized one. Start. So now, the next line is going to be this one here, so let's do a step command. So to execute, let me find the section that, here we go, stepping. So what stepping does is you type step by itself, and that will execute the next statement. So you can just execute one statement at a time. If you say step in, it'll execute in lines of code. Now, when you are stepping, if I have a line of code, and then a function call, let's say. If I'm stepping, I'll do this line, then I step again, it'll do that line, and then I step again, which is the function call. It'll transfer me to the function, and then I can step through the function one line at a time. When you hit the function call and you hit step, it'll transfer control to the function, and it will stop on the first line. And then when you hit step, it'll execute that first line. Now sometimes you don't want to execute a function. Like, let's suppose I've got a function call to a function which I've already debugged and I know there's no problems there. So I don't want to step into that function because that's just going to kill time. If you don't want to step into the function, you still want to call the function, but you don't want to step through it. Then you can use the next command. And next does the same thing as step, except next jumps over function calls. So it'll execute the function just like it was executing it when you run it, but it doesn't step through it. So let's try stepping here. Now in theory, this array variable just got allocated in memory, and it should be initialized. So let's look at the value of array and see where it's at in memory and what values are there. Because that's one of the things, primary uses of a debugger, is so that you can stop the program and you can examine variables. Because what you're looking for is, a bug. You're looking for a variable oftentimes that's getting changed to an incorrect value. So to examine here we go, examining array variables. So if A is an array, then P, which stands for print, PA would print the address in memory of the beginning of the array. So let's try P array. And so my array variable here starts in memory at that address. Now my array is an array of ints. It has 10 elements. And by default, an int is going to be 4 bytes of memory. So that means this entire array will take up 40 bytes of memory. So it starts here and takes up 40 bytes. And if I want to examine that memory, let's see. You do P, this syntax. It's kind of nasty. You do P and then star, the name of the array that you want to examine, and then you do at length. And then that will display length elements. So let's try that out. P star, the name of my array, at, and let's display the first 3 elements. And they're 1, 2, 3, like they should be. And if we want to display the entire array, we can do that. So during debugging, you might do that, and you might discover that one of these array elements isn't correct. It's wrong. Okay, so that'll help lead you to where the bug's at. If you just want to print the value of a regular variable, let's step again. the next line of code is going to read the value of A. So let's step. Now notice that GDB's sort of just hung up right now. It's waiting for me to type input. So I'm going to type in 100 and then press enter. And now let's look at the value of variable A. I think the command, it's been a while since I've used GDB. Yeah, just P variable, print for variable. So PA will display the value of A, which is 100. And now if I step again, it'll ask for B, and I can say, what's B? Now I've got a function call. So now if I do step, it's going to transfer me from main into sum. If I do next, it'll just jump over. It'll execute sum, which will return a value and stick it into the variable. So let's step into it. And if I do a list command, my current line of code is line number 5, which happens to be the first statement in sum. And now I can step again, and then I can print out the value of variable s to make sure that my function's returning the value I expect it to. And then step again will return me, and then I have to step one more time because I'm basically sitting at this brace, and I need to step one more time to return back to main. Yes, it's the line that will be executed next. Yep. So we can print variables, we can step, we can do next. You can examine memory. So X allows you to examine memory. You give it an address, and it'll display the memory there. And there's arguments to X. So by default, it'll display the value that's at this memory address. If I want to display that value plus a range of values, I want to display a block of memory to see what's there. There's various ways you can do that. If I wanted to display, remember I said my array's 40 bytes? So if I do x/40b and give it the address of my array, then it will display the contents of my array. Yeah, let's do that. What was my array address? There it is right there, right? The 60. Yep, let's try this. So if we do x, what's the syntax? /40b, and then that address. Are you familiar with hex and binary? Oh, okay. Yeah, because most often when you're talking about memory and programming, most often memory addresses are displayed in hex rather than decimal. Almost always. So that's 0x is how you specify a hex number in C++. I don't know if you knew that. Yeah, okay. Mm-hmm. Yeah. Let me show you. Okay. I'm happy to explain it if you want to. Anyway, there's my array. Now my array, remember, was 1, 2, 3, 4, 5, 6, 7, 8, 9. Where are these zeros coming from? These are bytes. That's right. So this is that byte, that byte, that byte, and that byte is array element 0. And then the next 4 bytes are array element 1. Now, you can also display, instead of bytes, you can display what are called words. And word is a term that you'll learn in EE 230. But a processor has a word size. The word size is a certain number of bits. And if today processors are generally going to be 32 bits or 64 bits, although you can get smaller 16 and 8-bit processors still, because they're used in embedded systems a lot. So the word size is sort of difficult to define because it's based on different parameters that are specific to that particular processor. But in general, a word on a system like ours is going to be 4 bytes. So instead of displaying bytes, darn it, I hit the wrong key. Bytes. Bytes, yeah. 4 bytes, bytes, 32 bits, yep. I thought there was an option. Oh, there it is. If I don't do 4B, if I do just X, and then I can specify the number of words. And it says here a word is 4 bytes. So if I do X 10, and then my array address, I thought that would display it differently. I was assuming it would print 0001, like it would put these 4 individual bytes together and display them just as one value. That's what I thought it would do, but it's not doing that. Anyway, oh, one thing you can do too, while we're on the subject of GDB, is you've got all these binaries in user bin. You're not going to have debugging information, but let's see, let's go to bin. The ls command is in bin. So we can gdb ls. Now notice it says here, reading symbols from blah, 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 no debugging symbols found. That's because when they built ls, they didn't do the -G option. And like I said, you don't normally put debugging information in production code. But we can still look at the code. It's just that it's going to be, let's see. Well, we can disassemble it. Well, we can't. I got to do start first. There you go. And you can study the assembly language code if you wanted to. And I can still step through this, I believe. But I don't have any debugging information. Boy, I don't know what that did. That was fun. I think I just killed GDB. Yep, I don't know. I killed it. In theory, oh yeah, so it just ran the command, and that what I'm seeing is the ls. Yeah, okay. I thought it would step and execute one assembly language instruction, and then I could step through them. I think there's a way to be able to do that. I'm not sure how, off the top of my head. So let's finish GDB here. What else? The main things you need to know are, I don't worry about listing source code too much because I just open the source code that I'm debugging in a separate editor window. Examining assembly language code, that'll be useful perhaps when you take EE 230. Examining data and variables, that's important to know. Examining memory can be very useful at certain times, so knowing that's good. Examining array variables is useful. Watches and displays. What a watch does is you can add a variable to a watch list. So you can say add variable A to the watch list. And then you can set it up so that when variable A changes value, your program will stop executing. And you can see where you're at and who changed the value of that variable. So if a variable is getting changed inadvertently, a bug, then you can set a watch on that variable. When the value gets changed, your program will stop, and you can say, where am I at, and what line of code just changed the value of this variable. Yeah, yeah. So watches are extremely helpful. And then what a display is a display in GDB is every time the program executes a statement, you can set up a display and it'll display certain information after every step. So this one's kind of useful if you're debugging assembly language code. If you do display /i $PC, then the PC register, and you'll learn this in E230, PC stands for program counter. And the program counter register, and every microprocessor has a register like this. But the program counter register always stores the address of the instruction that's going to be executed next. So if you're debugging assembly language code, which I'm going to go back to my home directory where I was at. I'll just show you this for the program that we have. So I'm going to load my programs, my unoptimized program again. And then start. And now I'm going to do this display /i $PC. So notice what happened. It displayed the instruction, the machine language or assembly language instruction, which is address 400997. Now if I do step, I stepped through that instruction, and now it's executing that instruction. And if I do step, it's waiting for me now to type in the value of A. And notice how every time it stops and displays the assembly language instruction that's going to be executed. So that's kind of useful, especially when you're debugging assembly language code. You can examine the processor registers. So a processor has registers, which are memory locations within the processor. So if you do info registers, this is an Intel Core Light chip. So in Intel, you have the register AX. You have a register called BX, CX, DX, SI, DI. So these are the processor registers, and it's displaying. I believe the first number is the contents of the register, but I'm not sure what the second number is. But if you're debugging assembly language code, you're dealing with registers and you need to know what values are in the registers, so that's useful for that. Yeah. Yeah. GDB by itself is kind of primitive. Jeff, I've not heard of. The one that I specified in the document after this chapter, in chapter 15, I have DDD. So I have a little section on debugging with DDD. What DDD and Jeff, like he mentioned, what these are basically is they have a graphical front-end interface, so it's more user-friendly. And on the back end, all they do is just call GDB and do commands. So you're still using GDB and debugging, but it has a nice user interface in front of it. And so if I were going to spend a lot of time debugging code, I would spend the time to learn DDD or set up some other graphical debugging. You're still using GDB, it's just that GDB is kind of difficult to use. We got started on this because I was talking about redirecting I/O. So let me finish that section on redirecting. So what I wanted to show you, and let me fix my program because I've made so many changes to it. I'm going to get rid of this. Okay. So my program is going to read two numbers and then print out the results to standard output. So I'll save that. I'm going to compile. And if I run it, it'll ask me to enter a number, another number, and prints out the output. If I want to send the output to a file, then I can use this, this symbol redirect standard output. And so you give it a file name, and now the output is going to go to the file name. Like that. Good. Yeah. Now you can also redirect standard in. So instead of typing the numbers at the keyboard, let's suppose I have the numbers in a file. Then when I run my program, I can tell it to read the input from my input file. Yes. So let's try this. And notice that it read the input, but it sent the output to standard out. Now if I also want to send the output to a file, then I can redirect both standard in and standard out. And now I don't see anything because it read from standard input from the file and it sent the output to the file. Now what pipe does is it allows you, and you can also redirect standard, this is chapter 9, just for completeness so that you're aware of it. You can also redirect standard error. Standard error is like standard out in that what you send to standard error will be displayed on the console window. But what standard out is what you're supposed to use for regular output, just displaying stuff. Standard error is designed to handle error messages. So if you have a command and you're redirecting standard out, and you also want to redirect standard error to the same file, then I can put a 2 here. And then that will redirect standard error to the file as well. Now that was weird, that didn't. Why did that send the output to the console? Yeah, I should be in bash. You do 2 greater than. Well, let me try it this way. That works. So you can do this. This redirects standard out to file name, and then it redirects standard error to errors. But usually I'm able to put a 2 there like that and make this work. But I must be doing something wrong. Normally you don't really have to mess with redirecting standard error. Piping, what pipe does is it allows you to take the output from one program and make it the input to another program. So let's do this. Let's modify our program. And I'm going to have the program read A and B, compute the sum, and then I'm just going to have the program output the sum. Like that. I'm going to save that. I'm going to create another program. And I'm going to make this program read a number from standard input. And then let's just make this function do something. I'm going to write a function that cubes a number. So I'm going to read an input from standard in, and then I'm going to pass that number off to cube. And then I'm going to print out what the value that it returns. Okay. So this program will read one number from standard in, compute the cube of the number, and then send it to standard out. So let's save that. Now, I'm going to build both of these. And then the second one. I got a syntax error. Oh, I forgot the standard colon part. So now I've got a program that prints out the sum. I've got another program that reads an integer and prints out the cube of the integer. So let's run the first program, which will spit out the sum of the two numbers we enter. And let's send the output from program to be the input to program 2. So we can run program, and we're going to pipe the output to program 2. So you use a vertical bar symbol like that. So now it's running program 1, and program 1's waiting for me to type two numbers. Now it's going to compute the sum and print it out, but that sum is going to become the input to program 2, which reads a number and cubes it. So Unix was designed such that there were lots of these. Unix was designed with the philosophy that you would have like system tools that you use to administer your system and stuff. It was designed so that the programs you had these programs that did one thing, but you could connect these programs together with pipes and make, I'm not explaining this well. I'm trying to think of an example, but it was basically designed so that you could pipe output from one program to become the input to another program, so that you could link these various commands together to perform some operation. Greater than redirects standard out, and less than redirects standard in. So let's modify this so that I'm going to read my numbers. Remember, I have this file called the numbers. Let's set this up so that program 1 will read its input from the numbers instead of waiting for me to type them at the keyboard. So it's going to read those two numbers, add them together, print out the sum, which will become the input to program 2, and let's send the output from program 2 to a file we'll call output. So now if we look at output, notice that it's got, that's weird. Oh, let's look. I was trying to figure out why I got different values. Well, I got different values because there I entered 100 and 200, and then there I only entered 10 and 20. So, but anyway, that command there, if you understand that, that's good. Piping, redirecting, very useful. Yeah. It's been around an hour or so, so we'll stop here in a little bit. But before we do, I want to ask you if you have any questions or anything you want me to go over. Yeah. Good idea. That's good. That's a good question. Let me flip through the document that I wrote for my class and see if there's anything in there I would recommend that you look at in addition to what we have covered. I'm just going to the table of contents. The first couple of chapters, first 3 chapters, first 4, there's nothing really in there. Probably all of chapter 5, because chapter 5 introduces the basic commands like copying files, making directories, and stuff like that. Are you familiar with what are called tarballs? Okay. Are you familiar with tar? Okay. That's probably something worthwhile to study. In section 515 on page 35, I've got a section that discusses that. So let's go to that section. So suppose, here's the example. I've got these files in my directory, and I want to create an archive, like a zip file, an archive. The standard way of creating an archive in Unix and Linux is to use a command which is called tar. tar stands for tape archive. And in the old days, at the time Unix was developed, hard drives were still not widely popular in those days, and they were very expensive. So a lot of systems just used tape to store data. You could back up the system on tape. And tape was just cassette tape, just like cassette tape. So TAR stands for tape archive. It's used for more than that nowadays. tar is kind of a complicated command, so if you do man tar, you can figure out all the details and everything, and it's got 1,000 options. The basic command is, let's suppose I want to create an archive of all of this directory, all of these files. So you can do tar. C stands for create. V stands for be verbose. I'll show you what that does. Oh, you know? Okay. And F stands for file. So the F option or command is followed by the name of the tar file that you want to create. If you don't do F and then give it the name of the tar file, does it send the output to standard output? tar? If you don't specify a file name for a tar file name, does it send the output to? That was my other thought. Yeah. Anyway, I always specify a tar file name. And then you specify the files that you want to add to the archive. So let's do this. Let's do tar cdf. And then let's tar up my CPP files. So I can just do that. And then what happened here? Oh, I didn't, I got to specify the name of the tar archive. So these are my source code. And a tar file usually has a .tar extension. So now, with tar, you can do a, I think it's T. Yeah, T. T stands for table or something, table of contents. If you do tar tf and then give it the tar file name, it'll list the contents, what files are in the tar. Now, a tar file is not compressed. It's simply, all it does is it takes the first program and the second program and it puts them into one file. So it simply takes multiple files, combines them all together, and creates one tar file. But it's not compressed. If you want to compress it, then you can specify another command, and you use Z if you want to compress it using zip. So then if I do a Z here, let's see what happens. Did it work? Oh, I'm sorry. It did compress it. Usually what I do is if I'm going to have a compressed file that's in zip format, I would name it .tar.zip. There we go. And then that's a zip file, so I've got an unzip command on my computer, so in theory I should be able to unzip that. In Ubuntu, it's a package that you can install. You do sudo apt-get install unzip, and then you can do sudo apt-get install zip. For some reason, I'm doing something wrong. I was trying to find out. Here you go. There we go. So to zip a tar file, here we go. I thought I did that right. This says create, compress using zip. This is the name of the tar file. That's a directory that we want to tar up. There's a command called file in Linux. So if you type file and then you give it a file, so I'm going to give it my supposedly what is supposed to be a zip file. What file does is it'll look at the file and try to determine what type of file this is. Is it a Word document? Is it a LibreOffice document? Whatever. So if I do that, it tells me that this is a gzip compressed data file. So it is a zip file. It is a zip file. Now, there's different compression utilities, and zip is one, maybe the most popular one, but there's another one that's used in the Linux world called bzip. Bzip generally compresses files more than zip does. So if you want to compress your file instead of creating a zip archive, if I wanted to create a bzip archive, then instead of putting Z there, I would put, I think it's J. Yeah, J. And then I would give my file a bz2 extension. This is actually bzip version 2. So bz2 means that it's zipped with bzip version 2. And then I got an error. Cannot exact, no such file. I'm just not having any luck tonight. I'm not sure what that message is, why that's happening. I don't know why that's happening because that seems to be like the correct command. Did it create the file? Yeah, I've got a bz2 file there. If I do file, then file tells me that it's empty. I have an empty bzip file. So there's something wrong with my command. But I'm not sure what I'm doing wrong. It may be something with general. I know this works on my own laptop. Anyway, when you create the tar file and then compress it, we call that a tarball. And a lot of Linux programs, like the ones that you can download from the internet and install, a lot of times you download tarballs. And so if you've got a tarball, then you want to, maybe it's a program that you want to run. So suppose I've got a tarball and it's a program I want to run, and I want to install this in my local home directory here. So then, given the tarball, if you want to extract the contents of the tarball, there's another command you use, which is X for extract. So here I've, let's see, I've created a tarball named that. It contains those 3 files, and then now I guess I don't have it here, but anyway, once I've created that tarball, oh, here I did. I'm sorry. So I created the tarball. This extracts it. Yeah. So that command right there extracts the contents. That's like unzip. Yeah. And it'll extract the contents to the current directory. So I mentioned tarballs primarily because a lot of programs come down from the internet as a tarball. And so you need to be able to extract it. So that's important to know. You may have, yeah. Yeah. What else in the table of contents should I mention? This is important to understand your path. So there's, in Bash, you have an environment and you have variables associated with it, and those are called environment variables. And one of your environment variables is capital path. And path contains a list of directories, and when you type a command, Bash will go through that list of directories looking for the file that matches the command you typed. So you can view your path if you do set capital path. Oh, that doesn't work. I usually just do set. Let's do set pipe. So I'm going to do the set command, pipe the output, and I'm going to feed the output into grep. Grep, remember, you give it a pattern and it'll tell you where that pattern's at. So I'm going to grep and search for path. There we go. So that's my path variable. And you can edit that. Is that echo works? Echo path? You got to do the $sign. Yeah, I didn't know that. Okay, good. I've always just done set. Sometimes you need to edit this path. So suppose you install in your local home directory a program called foo. And you want foo to be in your path because you want to be able to type foo. Or you want the directory where foo is at in your path because you want to be able to type foo and have bash find the binary. So currently, suppose foo is in my local home directory. Currently, there's not a path to foo. But I could edit this, and one way you can do that is, well, you can do it this way. When you log into Bash, or when you open a terminal window, there are some hidden files. And, oh, that's no good. One of those hidden files, the hidden files are the ones that start with dot. Bash RC. You'll have a .bash profile, and then you'll probably have a .bash RC file. You can edit the .bash RC file, and let's try that out on your computer. Do you have a a .bash RC file? Yeah. It'll be in your home directory.
Oh.
Yeah, so you would have to switch to your home directory. You can just do CD to switch to your home directory if you wanted to do that. Oh, push D, pop D. I should have told you that before you switched your home your home directory. So let's say I'm in directory here, and I want to go to that directory. You can do a push D, and that creates a list of the directories. And so when you do push D, it's like it'll save the directory you're currently in and then switch you to the new directory. And then when you're done doing whatever you wanted to do in the new directory, you can do a pop D command, and that'll go through this list and return you back to the directory you were at. I think it's push D and then space and then a directory you want to switch to. Yeah, it's push D and then dir, I think. Oh, no, wait a minute. Adds dir to the directory stack at the top. Yeah, try that, I guess. So now you're in Documents, and popd should return you back to your home directory. So that's kind of convenient when you want to temporarily go somewhere else and do something, but you want to return back to where you were originally at. Now go to your home directory and do an ls-a there, and you should see .bash rc. And if you cat .bash rc, is there anything in that file? There you go. So you can edit this file. You can add anything you want to it. What happens is when you log in, this file, the commands in it will be executed. Yeah. All .bash profile does is call this one though. Oh, .profile, yeah. Yeah. So anyway, you could put a command in here that says path equals whatever list of directories you want your path to be. And then when you log in, this commands will get executed and your path will be set up. So knowing how to change the path is useful when you're installing programs. Oftentimes when you're installing programs from tarballs. Yes. There's a file you can create in your home directory. I think it's dircallers.txt. Kali may be different. How's it? Can you show me what you did? I'm just curious. Oh, that's changing the color. That's setting up your prompt. Yeah.
Yeah.
Oh, here you go. Yeah, so you've got color set up. Yeah. So when you do ls-color, I think it looks for a file called dircallers.txt or something like that. Or you can name the file that you want it to use. But you can set that up so you can specify, for example, that you want CPP files to be displayed in red and doc files to be displayed in green. That's just eye candy. Let's finish this up. There's a chapter on VI if you want to learn VI. I've just introduced the basics. I've got chapter 12 on bash shell scripting, so if you wanted to start learning some shell scripting, that'll get you started. It's not everything. We talked about the GCC stuff, so there's that. Debugging. And then I've got a chapter on using Mercurial version control. I was using Mercurial at the time. Well, it was Python based. And I was using it at a time when I was doing some Python stuff. And my second edition of this book, or third or fourth or whatever edition I'm up to, I'm going to add a chapter on Git. Yeah. What version control does, this is source code management. SCM is the term that's often used, but version control. What it does is it allows you to, it's like a repository where you can add, say, source code files. And so you're working on a project, and you want to try something out, let's say, but you're not sure if it's going to work. And if it doesn't work, you want to go back to the original version of the file that you had. So you can add the file to the repository, and it'll be stored there. And then you can create a branch, and it'll make a copy of the file, essentially, and you can make your changes to it. And if those changes don't work out for whatever reason, you've still got the original copy of the file there. So it allows you to basically keep copies or different versions of the file, and it manages all that for you. If you're going to bother to learn version control, you should learn to use Git. So that's basically it. GitHub's just a hosting site, isn't it? Yeah. Yeah, you can keep the repository locally, but you can also have it essentially backed up. Right. Yeah, you can just run Git even when you're not online. Yeah. It's useful to know because a lot of open source software, the way you run it is you download, pull the software from the Git repository and then build it. So knowing how to do that's kind of too. Yeah. You mean using GitHub? Yeah. Oh, it's terribly complicated.